So we have seen the definition of the hydraulic efficiency. Hydraulic efficiency, it is given as a ratio of runner power to water power. We know there are three types of powers in case of a hydraulic turbine. One is input power, that is also called as the water power, then runner power, and last one is a shaft power. Okay, so in between water power and runner power there is hydraulic efficiency, and in between runner power and shaft power there is a mechanical efficiency, and then there is a overall efficiency that we have seen. So next definition, let us see quickly mechanical efficiency. Mechanical efficiency is nothing but it is the ratio of shaft power to the runner power, and after that there is a volumetric efficiency is also there, that is nothing but the leakage loss. Because of that there is a volumetric efficiency, actual volume of water striking the runner to the volume of water supplied by the runner, supplied to the turbine. So volumetric efficiency most of the times it is 100%, so it is not taken into consideration. So there is only mechanical efficiency and hydraulic efficiency. We have seen overall efficiency, it is the ratio of shaft power to the water power, output upon input. Output is shaft power, input is water power. So if you multiply and divide, if you multiply by runner power and divide by runner power to this shaft power upon water power, you will get shaft power upon runner power as a mechanical efficiency and runner power upon water power as a hydraulic efficiency. So overall efficiency is nothing but the multiplication of mechanical efficiency and hydraulic efficiency, that we have covered in impulse turbine also. Now let us quickly move towards the next part which we were looking at, that is called as the degree of reaction. Now the main part which is differentiating between impulse turbine and reaction turbine, that is the degree of reaction. Here the things will be clear to you. What is the basic definition of degree of reaction? Now I have told you, in case of impulse turbine there is only that total pressure energy is converted to kinetic energy at the inlet of the nozzle or at the exit of the nozzle, while in case of reaction turbine the pressure energy is converted partially into kinetic energy and pressure energy. That's why the remaining pressure energy is going to be converted into kinetic energy inside the runner. Okay, so there is a decrement in pressure across the runner, while there is no decrement of pressure in case of impulse turbine across the runner. So that causes the main difference between the impulse and reaction turbine. So let us see what is the definition of degree of reaction. Degree of reaction is defined as the ratio of pressure energy change inside a runner to the total energy change inside the runner. Now inside the runner there is a whatever is the change of energy, okay, that will have occur because of pressure energy and kinetic energy, while whatever is the contribution from pressure energy side, that divided by total energy change, that will be called as a degree of reaction. Okay, change in total energy is nothing but the total head across the water turbine, that is nothing but Euler's head, which is Euler's equation, 1 by G VW1 U1 plus minus VW2 U2. So that is the Euler's equation. This is also called as the Euler's head. Okay, this is the total energy. Okay, now let us see the degree of reaction derivation. Before that, let us see the velocity diagram for the reaction turbine. Okay, for a particular reaction turbine, if you see, this is the inward type of reaction turbine, radial flow reaction turbine. So this is water coming in, okay, and it is going out, okay, at point E. So at point B it is entering into the runner, at point E it is leaving the runner. So at point B, okay, when it is entering at some angle alpha, okay, it is nothing but the absolute velocity angle or the jet angle. So it is V1, okay, V1 is the absolute velocity and the angle made by V1 with horizontal is alpha. Similarly VR1 is a relative velocity making an angle theta, because V1 is making an angle alpha, that's why VR1 has to make an angle theta. U1, it is the linear velocity of the runner, okay, it is at the inlet, it is U1. So the in between VF1, that is nothing but the, here in case of this radial flow turbine, VF1 represents the radial flow velocity, or it is also called the flow velocity. So radial velocity inside this runner, and VF1 and V1, in between that there is a VW1. Okay, so this is very important for the and in between V1 and VR1 there is a U1. So remember, in between V1 and VF1 there is VW1, and in between V1 and VR1 there is U1. Okay, that's why this velocity diagram most of the students find it difficult to remember. How will you remember that velocity diagram? If you say V1, it is making an angle alpha with horizontal, VR1 making an angle theta with horizontal. In between V1 and VR1 you have to take U1, and in between V1 and VF1 you have to take VW1. This is very important. You have to take V1 as a constant. With respect to V1 only you have to take the position of U1 and VW1. V1 VR1 U1, V1 VF1 VW1. So in between V1 and VR1 there is U1, in between V1 and VF1 there is VW1. Okay, so likewise you have to remember. For outlet velocity triangle also, if you see the outlet velocity triangle, as it is coming out, so it is not coming with the velocity V2. Okay, when it is entering to the runner vane, that entry is tangential entry is of VR1. Similarly, tangential exit is VR2. So the velocity which is coming out at the same angle as that of the tangent to the runner is VR2, and same angle as that of the tangent to the runner at inlet is VR1. Okay, so theta and phi, they are also called as the runner angles, okay, or blade angles. Remember, that's why they are so shaped that they will be, the blade is designed such that it is at inlet it is having angle theta, and at outlet it is having angle phi. So VR1 and VR2, these are the entry and exit velocity for the running vane. Okay, then VR2 it is obviously it is making an angle phi, and V2 it is making an angle beta. Okay, in between V2 and VR2, again like V1 and VR1 there is U1. So here also V2 and VR2 there is U2. V2 and VR2 there is U2. Similarly V2 and VF2 there will be VW2, because here V1 and VF1 there is VW1. So here V2 and VF2 there will be VW2. So likewise it will be very easy to remember. If you see VF1 is a radial velocity. It is going along the radial direction. If you see VF2, it is a radial velocity, so it is going along the radial direction. Okay, at inlet as well as outlet. If it is going along the axial direction, then it will be called as the axial velocity in case of axial flow turbines. So it is radial flow turbine, that's why it is called as a radial flow velocity. Okay, so that we'll see afterwards. For the time being, you remember the velocity diagram very correctly. Okay, now let us see the degree of reaction derivation. Okay, how will you find the degree of reaction? Now if you remember the trigonometry, okay, from this inlet velocity triangle as well as outlet velocity triangle, we are going to use some trigonometry relation. So now we shall apply a simple geometrical relation, which is nothing but your cosine rule. We are going to apply the cosine rule for inlet as well as outlet velocity triangle. So if you see the inlet velocity triangle, okay, so if you remember, if you take angle alpha and apply cosine rule for this, then V1 square plus U1 square minus 2 times U1 2 times V1 into U1 into cosine of alpha will give you VR1 square. That is your cosine rule. Cosine rule tells you that if you want to find the square of this opposite side to that angle, that is VR1 square, that will be equal to V1 square plus U1 square minus 2 times V1 U1 cosine of alpha. Okay, the same thing is written here. VR1 square is equal to V1 square plus U1 square minus 2 U1 V1 cos alpha. So it will be nothing but you will take V1 square plus U1 square minus 2 times U1. What is V1 cos alpha? V1 cos alpha, if you see in this diagram, it is V1 cos alpha is nothing but VW1. So you can replace V1 cos alpha by VW1. So in short, you can write VR1 square as V1 square plus U1 square minus 2 U1 VW1. And that's why you can write U1 VW1 as 1 by 2 V1 square plus U1 square minus VR1 square. Alternately, similarly VR2 square. So if you see in this diagram, VR2 square, okay, that will be equal to now it will be cosine of 180 minus beta. If you see this, okay, this angle, so cos of 180 minus beta, it is minus cos beta by definition. So if you say VR2 square, it will be equal to V2 square plus U2 square minus of 2 times V2 into U2 into cos of 180 minus beta. So it will be ultimately VR2 square will be equal to V2 square plus U2 square minus of minus, it will become plus 2 times U2 into V2 into cosine of beta. Okay, cos of beta. But what is V2 cos beta? V2 cos beta will give you VW2. Like V1 cos alpha gives you VW1, V2 cos beta gives you VW2. So you can replace V2 cos beta by VW2. So you can write VR2 square is equal to V2 square plus U2 square. Okay. Okay. So it will be, now it should be a plus. It should be a plus 2 times U2 into VW2. So what will be U2 into VW2? Then it will be half. Okay. V2 square plus U2 square. Okay. Minus VR2 square, and there will be minus side outside. Okay. So if you simplify this and put this in Euler's equation, the value of VW2 U2 and VW1 U1, and simplify it, that is VW2 U2 and VW1 U1. So VW2 U2, it is minus of half V2 square plus U2 square minus VR2 square, and VW1 U1, it is half V1 square plus U1 square minus VR1 square. Okay. So if you put and simplify this in Euler's equation, which is head is equal to it can be given as VW1 U1 minus VW2 U2 upon G. Okay, for turbine it is written as VW1 U1 minus VW2 U2 upon G. Okay, you make a correction. This is a general term, but for turbine it is VW1 U1 minus VW2 U2 upon G. So VW1 U1, if you put, it is V1 square. Okay, half V1 square plus U1 square minus VR1 square. Okay, minus. Okay, minus half V2 square plus U2 square minus VR2 square. So this will be head. So when you simplify it, you will get head as 1 by 2G V1 square minus V2 square plus U1 square minus U2 square plus VR2 square minus VR1 square, because it was now minus minus, it becomes plus. Okay, it is minus VR2 square, so it will become plus VR2 square minus VR1 square, so it will be plus. So this is a reverse manner. Okay, so this you have to remember. Okay, now if you simplify this equation is an important form of Euler's equation. This is a Euler's equation, and this is also a form of Euler's equation. And if you compare this equation with Bernoulli's equation is nothing but P1 by rho g plus V1 square by 2g plus Z1 plus Q is equal to P2 by rho g plus V2 square by 2g plus Z2 plus W. Q and W we were neglecting. Okay, we were neglecting, but here W you have to take into consideration. Work is supplied, so you have to take work as nothing but the Euler's head, that you have to take as a head. And if you compare this, then you will get capital H is equal to P1 minus P2 by rho g plus V1 square minus V2 square by 2g. So here if you take W is equal to H and Z1 equal to Z2, Q is equal to 0, everything will cancel, and H will be equal to P1 minus P2 by rho g plus V1 square minus V2 square by 2g. And if you compare this equation number 2, which is H is equal to P1 by rho g minus P2 by rho g plus V1 square by 2g minus V2 square by 2g with equation number 1, okay, which is 1 by 2g V1 square minus V2 square plus V1 square minus U2 square plus VR2 square minus VR1 square upon 2g. If you compare this, then the first term is same. Okay, that is nothing but this V1 square minus V2 square upon 2g, and V1 square minus V2 square upon 2g is same, and H is also same. So only P1 minus P2 by rho g, it is also given as combination of these two terms. These two terms are representing the P1 minus P2 by rho g. So that is called as a pressure change, and this is called as a velocity change. This is kinetic energy change, and this is pressure energy change. So total head is represented as, this is called as, also called as a static head, and this is also called as a dynamic head. So static head and dynamic head. So static head, if you compare, it is given by this P1 minus P2 by rho g is given by this addition of these two terms, and the dynamic head is V1 square minus V2 square upon 2g. So in short, head is nothing but summation of dynamic head and static head. Out of that, the dynamic head is the nothing but the change in absolute velocity, and static head is nothing but change in pressure. Okay, and that is nothing but combination of these two velocities. And because of that, this relative proportion of energy transfer is giving you degree of reaction. We will continue this in the next lecture. Okay.